Hello, welcome to the last session of Unit 4. It is session 6. In this session, we are going to quantitatively determine the hardness of water. Let's look at the objective. By the end of this session, you should be able to determine the concentration of calcium ions or magnesium ions in hard water by back titration. Then we kick this off with a problem. Permanent hardness of water is determined by precipitating calcium ions and magnesium ions in the water by the action of excess standard sodium carbonate solution. A is a solution obtained by diluting 500 cubic centimeters of a saturated solution of sodium carbonate with 500 cubic centimeters of distilled water. B is a solution obtained by treating 500 cubic centimeters of saturated sodium carbonate solution with 500 cubic centimeters of hard water and filtering off all the insoluble precipitate. Before we proceed, let's look at something that would happen here. So look at this. It is sodium carbonate and we are using distilled water. So we don't expect any of these ions present in the distilled water. It has been distilled. What it means is that we will have a pure sodium carbonate. We have not been given concentration of sodium carbonate, and so we will definitely find it in the problem, or we will be asked to find the concentration of this. Now, this same sodium bicarbonate we see it here, and this time round it is being treated with hard water where we expect these ions or one of these ions to be present, and if any of them is present, then the concentration of this one is not going to be the same. Remember, here we are using pure distilled water, and the concentration here should be the initial concentration we are starting with over here. Okay, so because there are ions present in the hard water, we don't expect to get the same concentration as we have here, because some of it will be consumed by the ions present by displacing the sodium over here. So it's a back titration where we have our initial concentration of this from this solution, and we will have an excess over here because we expect some of this to be consumed. The excess is what will react with the acid coming in, so we can proceed. There is a third solution, that is the acid. So before we look at the rest, it means that we are first going to titrate this acid against the first solution, that is solution A, to know the concentration of the pure carbonate. Then we'll do again with the second solution B to know the concentration of the carbonate that was left over after the ions in the hard water have consumed some. Okay, so we are to find the concentration of sodium carbonate. We are to find the concentration of sodium carbonate in A, in mole per cubic centimeters. We are to find the molar or the amount concentration of sodium carbonate also in B. We are to find the moles of sodium carbonate that reacted with the calcium ions. This one, we'll just find the difference between those two concentrations. And assuming that all the hardness in the water is due to calcium ions, calculate I, the concentration of calcium ions in mole per cubic decimeters. Here we'll write some equations and do some mole ratio, the same as what we are going to do here, the mass of the calcium carbonate. So we have been given volumes. assume that the average volume of C that reacted with the 25 cubic centimeters of A is 20, and that of C is 14.4. So let's start, and we are starting with the acid. We know its concentration and we know its volume. The concentration is 0.5 mole per dm cubed. There are two ways, or there are multiple ways of going by this. If we want to use formula, then we can say we will find the number of moles from N is equal to C times V. The C is the 0.5 and then the V is the 20. But here we are going by the first principle, so let's start with interpretation of the concentration. 0.5 mole per dm cube means that 1 dm cube contains 0.5. 1 dm cube is equivalent to 1000. So 1000 cubic centimeters contains 0.5 moles. If 1000 contains 0.5, then that 20 that was used will contain what? So we do this and we have 0.01 moles. Next is to look at the equation of reaction. We balance and look at mole ratio so that we can find the corresponding moles of the carbonate, the sodium carbonate. And from this balanced equation, the mole ratio is 2:1. 2 moles of the HCl will give us, or would react with 1 mole of the sodium carbonate. In other words, the moles of sodium carbonate is half that of the HCl, and so we have 0.005 moles of the sodium carbonate. This is the moles contained in the small volume that was used, that is the 25 that was pipetted. So if that 25 contains 0.005 moles, then 1000 would contain what? We are going to get 1000 times 0.005 over 25. That gives us 0.2 moles per dm cube of sodium carbonate of A. So with A, the concentration is 0.2 mole per decimeter cube. But since that's a pure solution, we expect the whole of that solution to be 0.2 moles per cubic decimeters. Let's look at the next question, II, and we are going to do same, so that, but here whatever we are going to do will be the excess. Now here also, if we were given the same concentration but the volume was 14, so if 1000 contains 0.5, then 14 would contain 14 times 0.5 over 1000. That gives us 0.0072 moles. So this is the moles of the acid that reacted with the sodium carbonate. And so we do, or we write a balanced equation to show the reaction between sodium carbonate and HCl. Once again, we have the same mole ratio as the first, which is 2 of HCl reacts with 1 of the sodium carbonate. So that of the sodium, most of sodium carbonate is half the HCl. That gives us 0.0036 moles. This is the number of moles contained. This is the number of moles of the sodium carbonate contained in the 25 cubic centimeters of the sodium carbonate solution that was pipetted. But this time round, because it was diluted with the hard water, we expect the corresponding concentration to be the excess. So if 25 contains 0.0036, then 1000 would contain 1000 times 0.0036 divided by 25, and that gives us 0.114 moles per dm cube of the sodium carbonate in B. So have we noticed any difference? In the first instance, when distilled water was used, we had 0.2. This time round, when hard water was used, we have 0.14. It means something has happened. we have had some of the sodium carbonate being consumed and there was a leftover. So this that we have here is the excess after the ions have taken some away. So to find the moles of carbonate that reacted with the calcium ions or that was consumed by the ions, we just have to subtract the excess from the initial, that is 0.2. So that gives us 0.056. So this is the moles of the sodium carbonate that reacted with the calcium ions. Now, to find the concentration of the calcium ions, we know this moles of the carbonate, so we can write an equation, then we do our mole ratio. In this balanced equation, calcium displaces sodium, and we have 1 mole of the calcium ions reacting with 1 mole of the sodium carbonate to produce 1 mole of the calcium carbonate and then 2 moles of sodium ions. So per the mole ratio, the moles of calcium ions will be the same or will be equivalent to the moles of the sodium carbonate, and so the moles of calcium ions is 0.056. If we know the moles, then we can find the concentration. The relation is amount over volume, or C is equal to N over V. We know the N, the number of moles here, and then the volume was 500 cubic centimeters. We convert into decimeters, and that gives us 0.5 cubic decimeters, and this division gives us 0.112 moles per decimeters cubed. So this is the concentration of the calcium ions. The next is to find the mass of the calcium carbonate. So that same equation, but this time around we are going to relate the ions to the carbonate, not the calcium carbonate. Alright, so the mole ratio is the same. We could have still related the sodium carbonate to the calcium carbonate and we'll still get the same thing. So if 1 mole of the calcium carbonate was produced from the reaction between 1 mole of sodium carbonate and 1 mole of calcium ions, then the moles of calcium carbonate is 0.056, same as the moles of the calcium ions, same as the moles of the sodium carbonate. Now that we know the moles, the next thing is to get our molar mass. The molar mass we can get from the atomic masses. Calcium is 40, carbon is 12, oxygen is 16. That gives us 100 grams per mole. We know our amount already. And to find the mass, we know that N is equal to small m over capital M. Amount is equal to mass over molar mass. We make mass the subject and we have amount times molar mass, and we have 5.6 grams of the calcium carbonate. I hope you enjoyed this session as we end with this self-assessment question.